Hi, my name is Thomas Hussert.
And my name is Brecht Katz. We're both senior lecturers at West University, where we teach game development. In this series, we'll teach you how to build a 3D puzzle game using the XNA framework. XNA is a managed framework by Microsoft that enables us to build games for PC, Xbox 360, and Windows Phone. In this series, we'll teach you how to build a puzzle game using XNA for PC, and will include the following subjects. We'll draw sprites, draw models, draw animated models, control our character using input, play audio, do collision, draw menus, and much more. In short, we'll teach you everything you need to know to start building games. All art in this series has been made by Lino Driege, except for the character that has been made by Mike Petasek.
We would also like to thank our reviewers, without whom this series wouldn't be what it is today.
This series consists of 8 sections. In the first section, we'll get started and install all the necessary tools and build our first app. In section 2, we'll cover 2D graphics, drawing sprites and images. In section 3, we'll draw 3D graphics and animate them. In section 4, we'll cover inputs, so control our main character. In section 5, we'll play some audio. In section 6, we'll finish a little framework we will then use to build our game. And section 7 and 8 are totally dedicated to building our own game. We hope that you enjoy this series and start by building games as soon as you finished it. Let's go to the next video where we will install all the necessary tools. In this video, we'll install the XNA framework and XNA Game Studio 4.0, which is our main development environment. We can download XNA Game Studio from the App Hub. But before we do that, we need to install Visual Studio 2010. This because XNA Game Studio is a plugin for Visual Studio. Note that it has to be the 2010 version of Visual Studio. You can download Visual Studio 2010 Express from the Microsoft website. We won't go through the installation as it's fairly simple. After Visual Studio is installed, we can go to the App Hub to download XNA Game Studio. If you go to create.msdn.com, you'll end up at the App Hub. There we can click on Xbox Live Indie Games to go to the Creators Club website. Once we're at the Creators Club website, we can go to Resources, Downloads to download the latest version of XNA Game Studio. If you already have a version of Visual Studio 2010, it will install all the necessary add-ins for that version. Note that the Creators Club website also has an education section that is filled with examples. Okay, if you finished installing this, we can go to the next video. In the next video, we'll create our first game, build and run it. In the previous section, we've installed all the necessary tools. In this section, we'll create our first game. I've gone ahead and loaded Visual Studio 2010, so you need to do the same thing. After Visual Studio is loaded, we can create a new project. We can do this by going to File, New, Project. A screen will appear. On the left-hand side, amongst the installed templates, you can find XNA Game Studio 4.0. It's below Visual C#. If you don't see it, go ahead and open up Visual C# and you will find XNA Game Studio 4.0. In the middle of the screen, you can see what type of games we can make. We can make phone games, Xbox games, or Windows games. In this case, we will make a Windows game. Go ahead and give a name to this project. In this case, we'll call it Our First Game. Then click OK. Now Visual Studio will create a solution for us. Once our solution is loaded, we can see that Game Studio created 2 projects for us. One is called Our First Game, and this will contain all of our code. The second one is called Our First Game Content. This will contain all our content, such as 2D graphics, 3D graphics, and audio files. It also created a class called Game1. This is our main game class and will be explained in the next video. We can now build our project by going to Build, Build Solution, or pressing F6. On the left lower corner, you will see that the build succeeded. If the build didn't succeed, you will see a list of errors above. We can then run our project by going to Debug, Start Debugging, or by pressing F5. Once we've started debugging, a new screen will pop up. It will have our first game as title and an empty cornflower blue background. This might not seem as much, but everything is set up for us to begin. Our render loop is set up and we can start adding content. So we created our first project, we've built it, and we've run it. In the next video, we're going to talk about the main game class. So it's time to explain the Game1 class that the XNA Game Studio created for us. It inherits from Microsoft.xna.framework.game, which is the base class for all of our games. It has two fields, one of type Graphics Device Manager and one of type Sprite Batch. The Graphics Device Manager manages the configuration of the graphics card. The Sprite Batch enables us to draw 2D graphics. In the constructor, we will create a new Graphics Device Manager. The constructor has one argument, being the game. In this case, that's game1, so this. We will also specify a root directory for our content. In this case, it will just be content. In the initialize, you can create all of your content. The initialize is only called once at the start of the game. The initialize is meant for initializing non-graphics related content. Another method is the load content. The load content is also called once at the start of the game. It already has some code, being the creation of our sprite batch. We can use the load content to load all our assets, being 2D assets, 3D assets, or sound. There's also a method called unload content. Like the name suggests, we can use it to unload our content. It is called once per game when you exit. In the real life, we won't be using this method that much. In the update, you will calculate all your game logic. For instance, if you want your player to move, you will calculate the new position of the player each frame in the update method. It has one argument of type gameTime. The gameTime holds the total game time, being the total amount of time the game has been running, along with the elapsed time since the last update call. The update already contains some code to exit the game. Finally, we have our draw method. It also has one argument of type gameTime. Note that this gameTime object contains the elapsed time since the last draw call. This because the frequency of draw calls is not necessarily the same as the frequency of update calls. If our game is running slow, for instance on limited hardware, it could be that the system decides to skip a draw call. In the draw method, we will draw all our graphics, being 2D graphics and 3D graphics. The first thing you'll do in the draw method is clear your graphics device. Clearing your graphics device is like wiping your slate, making sure your board is clean before you start drawing. So that's it for this section. We've installed all the tools we needed, created our first project, and explained the game class. In the next section, we'll cover 2D graphics. We'll draw sprites and move them over the screen. We'll also start creating our little framework we'll be using for our game. In the previous video, we've drawn 2D graphics. The problem is, we've written everything in our game class, and if we add a lot of objects, it can get cluttered. That's why we need to refactor our code and create a little framework. But before we do that, we have to explain the concept of a scene graph. The idea behind a scene graph is very simple. An object can have a list of children, and it can also have a parent. You can visualize it as follows. A hero can have a sword. The sword is a child of the hero. The hero can currently be driving a car. The car is the parent of the hero. That way, if we move the car, the hero and the sword will move along with him. So let's dive into the code. We've created a class called GameObject2D. This is the base class for all our 2D game objects. It has three properties. One, the parent of type GameObject2D. It also has a list of children also of type GameObject2D. Finally, it has a property that defines if the object is visible or not. In the constructor, we will initialize our list of children, and we will specify we can draw the object. Then we need to add methods that will enable us to add and remove children. In the add child, we will check if we are currently not containing the child, because we don't want to add it twice. And if we don't, we will add the child and set the parent. In the remove child, we will remove the child and set the parent to 0. Next, we need to patch through some methods. In a scene graph, a parent object is responsible for calling some methods on a child object. For instance, if you call initialize on the parent object, the parent is responsible for calling initialize on all of its children. So we will do that for the initialize, load content, update, and draw. Passing the code through is very simple. For instance, in the initialize, we loop over all of our children and initialize them as well. Note that the update and the draw method have one argument of type renderContext. This is a class we've created. It has 3 properties: the sprite batch, the graphics device, and the game time. The reason we've grouped these into one renderContext object is for extensibility. Later on, we can add different properties and all of our objects in the scene graph will have access to them. So now we've created our basic scene graph. Now it's time to add position, rotation, and scale to it. We'll do that in the next video. In the previous video, we've created our basic scene graph. Now it's time to add position, rotation, and scale. We need to make a difference between local space and world space. Like we mentioned in the previous video, position, rotation, and scale are relative to the parent. So for instance, if an object's local position is 1010, but the parent's position is 5050, then the world position of the object will be 6060. So we will need to add properties for world space and local space. First, we need to add properties for the local position and the world position. Both are of type vector2 because we have 2 axes, x and y. Note that the world position has a private setter. We will also do the same for the scale. Both will also be of type vector2. Then we will also add properties for the rotation. These will be of type float, because the rotation is an angle. We'll also create a property for the pivot point. The pivot point is a point we want to rotate about. For instance, if you have a sword, you don't want to rotate about the middle, but you want to rotate about the handle. Then we need to add a field of type matrix. This matrix, the world matrix, is a compiled version of the position, rotation, and scale. We use matrices because they're very handy for managing positions, rotations, and scale. We can just multiply them together and we don't need trigonometry. Next, we will need to add some methods to control the position, rotation, and scale. Note that these methods will only control the local rotation, position, and scale, because the world position, rotation, and scale will be calculated each update. These methods have several overloads. So then we can go to the update method. First, we will need to calculate our world position, rotation, and scale. We'll do this by creating our world matrix. The matrix class has a lot of helper methods. For instance, create translation, create scale, and create rotation. We can use those to build our world matrix. We need to do it in a specific order. First, we will translate to our pivot point, actually to the negative of our pivot point. Then we will scale the object, rotate it, and then translate it to the local position. We need to do it exactly in that order. If we were to translate first and then rotate, the object wouldn't rotate about the middle of the object, but it would rotate about the origin.
Let's take a look at the following illustration. If we rotate the hero first and then translate it, it will seem as if the hero is rotating about its origin or its pivot point. However, if you were to translate the hero first and then rotate it, it would rotate about the origin. Then, if we have a parent object, we will multiply our world matrix with the world matrix of the parent, so our position, rotation, and scale become relative to the parent. Now comes the tricky part. Our position, rotation, and scale are compiled in a matrix.
We need to get it out of there. We can use the decompose method to do that. If the decompose succeeded, we should have our position, rotation, and scale. The only problem is our rotation is a quaternion. We don't want the quaternion, we need a float. So we will need to transform it.
If you want more information on quaternions, you can take a look at the references that come with this section.
We can transform that quaternion to a float in 3 steps. First of all, we need to transform the unit vector for the x-axis with the rotation. That will give us a direction. We can use that direction and the arctangent create a rotation. If the result is a number, we can use that rotation as degrees. If it's not a number, we can just use no rotation at all. Finally, we're going to set our world position and world scale. That's it, our GameObject2D class is ready. In the next video, we will create a GameSprite class. We will use that class to draw sprites.
In the previous video, we've created our GameObject2D class. In this video, we will create the GameSprite class. We will use this class to draw the background and the hero. So let's go to the code. Our GameSprite class inherits from GameObject2D. This because a sprite is a 2D game object. It has a position, a rotation, and a scale, and it fits in the scene graph. It also has several fields. It has 2 fields for the texture, one being the path to the asset file, and the second being of type texture2D that will hold the texture. Next, we will expose 4 properties of the sprite batch draw method. We will expose the depth, the color, which we can use to tint the object, the sprite effect, which we can use to flip the object, and the rectangle. This draw rectangle will determine which part of the texture we will draw. Finally, we will create a width and a height property. These will return the texture width and the texture height. The constructor is simple. It has one argument, being the path to the asset file. We store that path and set the color and the effect to its default values. In the load content, we will load our texture using the content manager. In the draw method, we can then draw the object. If the object is visible, we can use the draw method of our sprite batch to render the sprite. We pass our texture, our world position, the draw rectangle, the color, the rotation, the scale, the effect, and the depth. That's it for the GameSprite class. Let's go to the game and draw our sprites. Okay, so in our game class, we will add 3 fields. One of type render context, that will hold our render context, and 2 of type GameSprite, one for the background and one for the hero. Then we will go to the initialize. In the initialize, we will create our render context, our background, and our hero. Then we can go to the load content. First, we will set the sprite batch and the graphics device property of our render context. Then, we will call load content on our hero and on our background. We will also set the local position of our hero. Then, in the update method, we will set the game time property of our render context. We will also call updates on our background and on our hero, passing our render context. Finally, we can go to the draw method. There, we can draw our hero and our background. We do that between the spritebatch.begin and spritebatch.end. If we then run our project, we will see our background and our hero located at the center bottom. That's it for this section. Let's go to the next section where we'll cover 3D.
In the previous section, we've installed all the necessary tools and created our first project. In this section, we're going to draw 2D sprites and move them over the screen. A sprite is also known as a texture, and in essence, it's just a plain image, like a PNG file. In this video, we're going to set up all our content so it's ready to be loaded. As you can see, we created a new solution called Loading and Sprites. The solution has 2 projects, Loading and Sprites and Loading and Sprites Content. Loading and Sprites Content will contain all of our assets. Those assets will then be compiled to an intermediate format called XNB. XNA does this so content loads faster in most cases rather than loading the raw files.
So let's add content to our project. There are two ways we can do this. The first is by right-clicking our content project and going to Add Existing Item, and then navigating to your content. The second way is to go to Explorer, select all our files, and drag and drop them into our solution. These two textures are the only ones we're going to use in this section. We can just select them all and drag and drop them into our content projects. You can see they get added to the content project automatically, and they also get copied in the appropriate folder. When we click on our hero texture, we can see several properties. First of all, our hero texture has a name. In this case, it's hero. We can use that name to load our texture through code. We can also see the texture has no extension, so no PNG. That's because the asset gets compiled to an intermediate file format called XMB. We can also specify a content importer and a content processor. An importer will convert our assets into the content documents objects model, a format that can be read by the processor. The processor will compile the asset into a managed code object, which can then be serialized into the intermediate XMB file format. We can see that our PNG file gets recognized as a texture, and XNA Game Studio automatically selects the texture importer and the texture processor for us. By default, XNA supports the following file types: BMP, DDS, DIB, HDR, JPEG, PFM, PNG, PPM, and TGA. It's also possible to write our own importers and our own processors, but that's beyond the scope of this section. If we now build our project, we can see that the content pipeline will compile all our assets. If we go to our game folder, we can find our assets in compiled XNB format. Okay, everything is set for us to start writing code. That's what we'll do in the next video. We'll draw some textures to the screen. In the previous video, we've added all our content to our content project and built it. Now it's time we draw some sprites. We need to create two fields for our textures. Both are of type texture2D. We call one background and call one hero. We can then load our textures in the loadContent method. There, we can use our textures using the content manager. We can access the content manager via this.content. The content manager has a generic method called load. Generic means we can specify a type, in this case texture2D. The load method has one argument, being the path to the asset. The path is the folder structure followed by the name. In this case, if we go to the properties, we can see that our background texture is named background, so we just specify background. We do the same for our hero texture. Instead, we use hero as argument. Now let's go back to the initialize. We want to change the size of our window. This is because our background has a resolution of 1280 by 720. By default, our window is going to start at 800 by 600, so we want to change that. We can do that in the initialize by using our graphics device manager. Our graphics device manager has a property called preferred back buffer width. We can use that property to set the width of our back buffer, so of our screen, in this case 1280. It also has a property called preferred back buffer height. We set that to 720. Then we want to apply the changes we've just made. We can do that by calling graphics.applyChanges. Then we can go to the draw method to draw our sprites. Drawing sprites is always done in a specific way. First, we need to call begin on our sprite batch. This sets all the correct states on our graphics card to draw 2D objects. So we are actually telling our graphics device that we are ready to draw 2D objects. Then we can draw all our objects using spritebatch.draw. After we've done this, we can call spritebatch.end to reset the states to the way they were before we called begin.
Using states, we can for instance enable transparency.
SpriteBatch.draw has several overloads. We will use the one that has a texture, a position, and a color as arguments. The first argument is a texture, being the texture we want to draw. In this case, we'll first draw the background. The second argument is a position. We'll draw the background at position 0, 0, which is the top left corner of our screen.
The x-axis is on the horizontal plane. So we start at the top left at 0 and we go up to 1280 as we go to the right. The y-axis is on the vertical plane. So we start at 0 at the top left corner and we go up to 720 as we go to the bottom.
So when we draw our background at 0, 0, we draw it at the top left corner of our screen. Finally, we can specify a tint color. If we pass color.white, we will not tint our objects. Then we can draw our hero. Note that we have to draw our hero after we draw our background. Order is important. If we draw our hero first and then our background will be in front of our hero. We don't want that, so we want to draw our background first and then our hero. We will position our hero at the center of the screen to the bottom. So, as x position, we take the width of the screen divided by 2. And as y position, we take the height of the screen minus the hero height. If we now run our project, we can see a background and our hero. In the next video, we're going to move our hero. So in the previous video, we've drawn 2D graphics. In this video, we're going to add some movement to the hero. The hero is going to walk right, and when he reaches the edge of the screen, he's going to turn back. We need to start by adding some fields. First of all, we'll add a field of type vector2 for the position. This will be the position of our hero. We'll also add a field of type integer that is the speed. How many pixels per second will our hero move? And finally, we will add another field of type integer being the direction. If the direction is 1, we'll move to the right. If the direction is -1, we'll move to the left. The rest of the action will go on in the update methods. First of all, we will calculate the direction. If we need to move to the left or to the right. If we are currently moving to the right, so if our direction is bigger than 0. And if we reach the right border, so the x position of the hero is bigger than 1280 minus the width of the hero, then we will change the direction and set it to -1. So we will move to the left the next frame. Otherwise, if we are currently moving to the left, so if the direction is smaller than 0, and the x position of the hero is smaller than 0 as well, so we reached the left border of the screen, we will set the direction to 1, meaning we will move to the right the next frame. So now we can calculate the amount of pixels we can move over the x-axis. The amount of movement is the speed, in this case 200 pixels per second, times the direction, left or right, times the elapsed time since the last update was called. We use this game time to make sure our game runs frame independently. So if our frame runs slower or faster, the hero movement will be the same. Then we will calculate our new position. Our new position is a new vector2, taking the old x position plus the movement we've just calculated. The y position is the same, as we will only move the hero horizontally. So now that we've calculated this position, we can go to the draw method and change the position of the hero there. We can do that in the SpriteBatch.draw method. We change the second argument with our _position. If we build and run, we will see the hero moving. There's only one issue. If he reaches the right border of the screen, he will turn back, but he'll be walking backwards. So let's do something about that. SpriteBatch.draw has several overloads. So in the draw method, we'll use another overload. The first argument will still be the texture, and the second will still be the position. The third argument will be a rectangle that defines which part of the texture we can draw. In our case, we don't need a rectangle, so we'll just pass null. The fourth argument is still the tint color, so color.white. Then we can pass a rotation. We don't want rotation, so we'll pass 0. Then the origin, which is also 0. Then the scale, which we will set to 1. We don't want to scale the object. And then we can pass a sprite effect. We can use that sprite effect to flip our sprite if we reached the right border. So, if our direction is bigger than 0, we won't use any sprite effect. If our direction is smaller than 0, we'll flip our sprite. If we build and run the game then, you'll see that our hero isn't moving backwards anymore. So we've written a lot of code, but it can get cluttered quite easily if we add more sprites. So in the next video, we'll refactor our code and make sure we have a clean design. That will help us when we have to build our game. In the previous section, we've covered 2D graphics. In this section, we'll cover 3D graphics. But before we start, we need to explain the 3D coordinate system and the concept of world, view, and projection. Just like working in 2D, working in 3D means using a certain axis system. Unlike 2D, our axis system doesn't originate at the top left corner. Because we'll be using a camera to view the scene, the origin of our axis system doesn't really matter that much, as we will see later when talking about the view matrix. The x-axis is on the horizontal plane, the y-axis is on the vertical plane, and the z-axis goes through our screen. This is known as a right-handed axis system. So we have 3 axes we can use to position our objects. To position our objects, we'll use matrices. The reason we use matrices is because we have the position, the rotation, and the scale of an object in one matrix. And matrices can be easily multiplied with one another. We won't go in detail about how a matrix works, but we will use them. And therefore, we need to know 3 concepts: world, view, and projection. The world matrix contains the position, the rotation, and the scale of an object. The view matrix contains the inverse of the camera's world matrix. This is because we will use the view matrix to transform our vertices so they are seen from the camera. The projection matrix contains the lens settings of our camera. If we want to position an object in a 3D world, we multiply it with the world matrix. Then it's positioned in 3D space. If we then multiply it with the view projection matrix, it will appear as if the object is seen through the camera. Let's take a look at an example. This is the normal situation of our game. We have our scene, and our camera is looking directly at it. If we want to view our scene from another angle, we can rotate our camera. We do this by changing the view matrix. If we want to zoom in or out, we can also do that by changing the lens settings. So we change the projection matrix and the scene is viewed from further away. Okay, I guess we covered the basics. Let's go to the next video and draw 3D models. So in the previous video, we've covered the 3D coordinate system and the concept of world, view, and projection. It's time we started drawing models. In our demo solution, we've added a model with vampire.x to our content project. As you can see, the model uses the X-file content importer and the model processor. This is the file we will load through code. By default, we can load FBX files and X files. Let's dive into the code. We need to add 3 fields first. One field of type model for our hero, and 2 fields for our camera. These will be of type matrix, and this will be our view and projection matrix. We can then go to the initialize. There, we will initialize our view and projection matrix. We can create our view matrix by using the createLookAt method from the static matrix class. It has 3 arguments. The first is the position of the camera. In this case, we will position the camera 20 units out of our screen.
The second argument is the look at. Where is the camera looking at? We will make the camera look at the origin. And the third is the up vector. For our projection, we can use perspective or orthogonal projection. With perspective, the size of the object changes depending on its depth. The further an object is away, the smaller it is. With orthogonal projection, an object still has the same size regardless of the distance. In this case, we will use an orthogonal projection. We can create our projection by using the create_orthographic method from the static matrix class. It has 4 arguments. The first is the width, the second is the height, the third is the near plane. Everything closer than the near plane will be invisible, and the last argument is the far plane. Everything behind the far plane will be invisible as well. Okay, we've just set up our camera. Let's load our hero in the load content. We can do that the same way we've loaded our content before, by using the load method on our content manager. We want to load a model, and which model do we want to load? The vampire. We can then go to the draw method to draw the model. Drawing the model is a bit of work. First of all, we need to copy all the bone transforms to a local matrix array. A model can have several bones. Each bone has its own world matrix. We need to store that to transform the vertices attached to that bone into 3D space. Once we've done that, we need to loop over all the meshes inside our model. Our model can have multiple meshes, so you can see these as models inside the models. Then, each mesh can have multiple effects. An effect is a program that runs on the graphics card that draws your model, so we need to loop over all the effects in our mesh. XNA has 5 built-in effects. First, basic effect, which is a very general effect. We can do lots of things with it. Skinned effect, that will help us do animations. Environment map effect, it will help with reflection. Dual texture effect, which we can use for shadow mapping, for instance. And alpha test effect. Alpha test effects enable transparency. For now, we will use basic effect. It's also possible to load your own effects, but that's beyond the scope of this series. While looping over all basic effects, we need to set some variables. First of all, we want to enable default lighting, so our object is lit. Then, we need to specify our view and projection matrix, so the effect knows where our camera is at. Finally, we also need to set the world matrix, so our effect knows where to position the object. We will currently use the world matrix of the parent bone as world matrix, so the object will be positioned at the origin. Finally, we can draw the mesh by calling mesh.draw. If we run the project now, we should see the model in the center of our screen. Okay, let's go to the next video where we will mix 2D and 3D. In the previous video, we've drawn a 3D model. In this video, we'll combine the 3D model with a 2D background. The basic setup is very similar to what we've done in the 2D section. We've created a background of type GameSprite. In the initialize, we made a new instance of it. In the load content, we called load content on it. And in the draw method, we've drawn the background between the begin and end of our sprite batch. Note that order is important here. If I want the background to appear behind the model, we have to draw the background first and then the model. Otherwise, the model would be behind the background. There are instances where we want the 2D graphics to be in front of the 3D graphics, for instance, a health bar. If you were to run the code now, we would get a strange looking model. That's because the spritebatch.end doesn't reset all states properly. We need to reset 3 states ourselves: the blend state, the depth stencil state, and the sampler state. If we reset these values and press F5, our model should appear in front of a background. In the next video, we'll refactor our code and create our base class for all our 3D objects. In the previous video, we've drawn our background and our hero in front of it. In this video, we'll create our GameObject3D class.
It's part of the framework we will use when building the game. The implementation will be very similar to the GameObject2D class. The GameObject3D class will have a parent-child system where we can add children to a certain object. Its position, rotation, and scale will then be relative to the parent. So let's go to the code. Here you can see our GameObject3D class. It's abstract because it's meant for inheritance. It has several fields. It stores the local position and the world position. The position is a vector 3. It also stores the rotation and the scale. The scale is also of type vector 3, and rotation is of type quaternion. A quaternion is a 4-dimensional vector. It has a direction and an angle. Then we have our parent, which is of type GameObject3D, and our list of children. Finally, we have our world matrix, which again is the compiled version of our position, rotation, and scale. In the constructor, we initialize our list of children and set our local scale and world scale to 1. We also have methods to add children and remove children. The implementation is very similar to the GameObject2D class. And then we also have methods to translate, so move the object, to scale the object, and to rotate the object. These methods have several overloads. Finally, we also have an initialize method, a load content method, an update method, and a draw method. In the initialize, load content, and draw method, we will just call the same method on our children. In the update method, we'll calculate our final world position, world rotation, and world scale. The implementation is similar to the one of GameObject2D. We will first build our world matrix. Therefore, we will use the helper methods of the matrix class. We will first rotate our object, then scale our object, and then translate our object. If we have a parent, then we will multiply our world matrix with the world matrix of the parent. That way, our position will be relative to the parent. Finally, we will decompose our matrix to get our final world position, world rotation, and world scale. That's it for our GameObject3D class. We've also created some other classes. For instance, the base camera class. The base camera class is a 3D game object, and it will hold our view matrix and our projection matrix. The implementation is very simple. We have two properties, one for the view matrix and one for the projection matrix. Our projection matrix is the same one we've been using in the previous example, an orthographic projection with a width of 1280 and a height of 720. We also have our view matrix. We will calculate our view matrix every frame in the update. We've also changed our render context class and added a property for the camera. That way we can pass our camera with our render context, and each object will have access to our view and projection. We've also updated our game class. We've added a field of type base camera, initialized it, and set the camera property of the render context to that camera. We also translate the camera, so it's at the same position as it was previously, 20 units in front of the screen. In the update, we update the camera, and of course, when we draw our model, we use the camera instead of the view and the projection. If we now run the project, we should have the exact same output as we had before. So we've created our base class. The implementation was very similar to that one of GameObject2D. As an extension to this video and a personal exercise, you could make a base class for the 2D and 3D objects called GameObjectBase. In the next video, we'll create our game model class. In the previous video, we've created a base class for all our 3D objects. In this video, we'll create our game model class. The game model class inherits from the GameObject3D. The implementation is very simple. We have two fields, one of type string, the path to the asset file, and one of type model. This is the model we will draw. In the constructor, we have one argument, being the path to the asset file. We will store that in our field. In the load content, we will use the content manager
to load the asset. And then finally, in the draw, we will draw the object. Drawing the 3D model is the same as we've done before. We copy all the transforms of our bones to a local matrix array. We loop over all the meshes. We loop over all the effects. We enable default lighting, set our view, projection and world matrix, and then draw the object. In this specific case, we've set more properties. We enabled alpha blending, so transparency. We said we preferred per pixel lighting instead of per vertex lighting, and we've set a specular color and specular power. Specular determines how shiny an object is. Let's go to the game class where we can use the game model. We've added a new field of type game model. We called it _hero. In the initialize, we created the new game model and added the path to the asset file, being vampire. In the loads content, we called loads content on our hero. In the update, we update our hero. And in the draw method, we draw our hero. We do this of course after we've reset the render states. If we run our project, we should have the same as before, but now our code is properly designed. In the next video, we'll animate our model.
In the previous video, we've created our game model class. In this video, we will draw an animated model and create our game animated model class. There's one problem. Animation isn't supported by default in XNA. However, there is a way to do it. There's a custom processor on the App Hub you can download. There's also a skinned model data project that holds an animation player. We've updated this animation player so it offers more functionality. We need to add these two projects to our solution. The skinned model pipeline project contains a processor. The processor will transform your model file into a code object. Therefore, we need to add a reference from our content project to the processor. We can do this via add reference. You can see we've already added the reference here. If you added the reference and we click on the vampire.x model, we can change the content processor. We used to use the model processor. Now we use the skinned model processor. We need to use this processor because otherwise we won't have access to the skinned model data. In our game project, we also need to add a reference to the skinned model data project, because we will need to access our animation player. Okay, everything is set up for us to begin. Let's go to our game animated model class. Our game animated model class inherits from game object 3D. This because our model is a 3D game object. It has several fields. First, the path to the asset file, and a field that will hold our model. We also store our animation player, which will play our animation, and our skinning data. Our skinning data contains all the data for the animation. We'll also store the speed scale. How fast do we want to play our animation? Then we have three other fields: the init clip name, init loop, and init blend time. The constructor is very simple. It has one argument, being the path to the asset file, and we'll store it. Just like in the game model class, we will load our model through the content manager. After that, we need to store our skinning data. The processor stores the skinning data in the tag of the model. So we transform the tag, which is object, to skinning data. If our skinning data is 0, then we have some issues, so we call debug.assert. Then we create a new animation player, passing our skinning data. This because the animation player needs to know all the animation information, and that's stored in our skinning data. We also set our animation speed. If our init clip name, so the clip we want to play to start with, is different from 0, we will play an animation. The class also has several methods to set the speed of the animation. This will just call the set animation speed on the animation player, and a method to play an animation. Playing an animation can also be done through the animation player. It has a method start clip that takes a clip, so an animation clip, a boolean that specifies if we should loop the clip, and a blend time for animation blending. There are other methods like the getBoneTransform method, where we can get a transform for a specific bone. This can be handy if you want to attach a sword to a hand, for instance. Then you can get the transform of the hand bone and attach the sword to that. In the update method, we will update the animation player, passing our render context game time and the world matrix. Finally, we can draw the object. In the draw method, we have to get all the transforms for each bone from the animation player. The animation player will move all the bones according to the animation, so we need to get the final world matrices for all our bones from the animation player. Then we can loop over all the meshes inside our model, the same way we did with the game model class. And then we can loop over all of our effects. Note that this time we are not using basic effects, but skinned effects. For animations, we need to use a different shader. First of all, we will set all the bone transforms. We'll enable default lighting and set our view and projection matrix. We will also set the specular color, power, and prefer per pixel lighting. Finally, we will draw the mesh. Okay, so let's go to the game class and use our game animated model. We've changed the type of our hero to game animated model. It used to be a game model. In the initialize, we also called the correct constructor. We also stated we wanted to play an animation called run. That's it. If we now run our project, our hero will be animated and he will be running. That's it for this section. In the next section, we'll cover input and add interactivity.
In the previous chapter, we've covered 3D graphics. By doing this, we can make pretty visualizations and simulations. But games also need interaction with the user. Therefore, we need to handle input from the user. In this chapter, we will cover 3 types of input: mouse input, keyboard input, and gamepad input. But before we start these topics, we need to create some kind of test environment. And that's what we are going to do now. The idea is very simple. It's an empty screen with a white dot in the center. Based on the input, the dot will move or change its color. We start by creating a new project. Call it input scene. This will be some kind of template that we use to test the input from different input devices. First of all, we need a white dot. We will use a texture for that. It's just an image of a white circle. I've already added this texture to the content project. We start with adding some fields. A texture 2D that holds our white dot, called white dot. A vector 2 that contains the position of the dot, called dot position. Another vector 2 that contains the middle of the screen, called window center. And also the color of the dot, called dot color. In the initialize method, we calculate the value of window center by taking the half of the width and height of the screen. We set the initial dot position to the center of the screen and dot color to white. Next, we need to load our white dot texture. We do that in the load content method. We use the content manager to load our white dot texture. It's of type texture2D and named white dot. Now we are ready to draw the white dot. We will use the sprite batch to draw our texture. But before we can do that, we have to call the spritebatch.begin method. This method sets all the correct render states for drawing 2D. And now we can draw our texture using the spritebatch.draw method. White dot as texture 2D, dot position as position, and we will also subtract the half of the width and height of the texture. This way, the center of the white dot will be the anchor point instead of the left top. And the last argument is the color. Don't forget to call spriteBits.end afterwards. When we build and run this game, we see a white dot positioned in the middle of the screen. In the following videos, we will manipulate this white dot using different types of input. In the next video, we will cover mouse input. In this video, we will use mouse input to manipulate the white dot. We start this demo with code from our empty input scene that we made in the previous video. XNA provides a static class called mouse. This class contains a method called getState. When we call this method, we retrieve an object of type mouseState. Let's have a look at the properties of that object. There are properties for the mouse buttons, a property that indicates the total scroll offset, and also an X and Y property, representing the current mouse position. Let's change the dot into a cursor. We can do that by changing its position to the position of the mouse. That's an easy task. Dot position equals new vector 2 mouseState.x and mouseState.y. Build and run. You can see that our white dot follows the mouse now. Now we will write some code that changes the color of the dot to red when we press the left mouse button. The type of the button properties is of type buttonState. This is an enumeration that contains two values, pressed or released. So for this example, the buttonState needs to be equal to pressed. If that's the case, we will set dot color to red. We also need to reset the dot color each frame. Otherwise, it stays red from the moment we press the button once. Build and run the game. When we press the red button, the dot's color changes to red and back to white when we release the button. We can also check if a button is released, but this is a special case. If a button is not pressed, its state will always be released. So we need a way to know if the button was pressed the frame before. This way, we can compare both states. If the mouse was pressed in the previous frame and is released this frame, we know that the user released the mouse. Let's create a new field of type mouseState. Call it previous mouseState. At the end of each update, we need to fill this field up with the current mouseState. This way, we have access to the previous mouseState in the next frame. When our left button was pressed in the previous frame and released this frame, then we will reposition the mouse to coordinates 100, 100. Setting the mouse position can be done with the setPosition method of the static mouse class. This method will move the mouse to its new position, being 100, 100. Build and run the game. When we press the left button, our dot turns red, but when we release the mouse, it turns white and jumps to the position 100, 100. The last thing we'll add is changing the color of the dot based on the current mouse scroll value, but the scroll wheel value is a special case. Normally, you would expect that the scroll wheel value changes with a value of 1, but this isn't the case. The change in value is equal to 120. They use the bigger values, such as 120, to allow Microsoft or other vendors to build finer resolution wheels in the future. The expectation is that such a device would send more messages per rotation, but with a smaller value in each message. So the value of scroll wheel value depends on the scroll resolution of the mouse. And that's the reason why it's a value of 120 and not 1. Time to write some code. We only want to use the scroll wheel when the right mouse button is being pressed. So now we want to change the color based on a certain amount of scroll steps. We'll add a local variable called scroll steps with a value of 12, meaning that our color is fully changed after 12 scrolls. Then we need to normalize our scroll wheel value. We'll assume that our scroll data is 120. So dividing the scroll wheel value of our current mouse state by 120 gives us a normalized value of our scroll wheel value, and we store that in a variable called normalized scroll wheel value. This normalized scroll wheel value will increase or decrease based on the scroll direction with a step of 1. Now, we can calculate our color component with these variables. Multiplying 255, which is the maximum value of our color component, with division of our normalized scroll wheel value by our scroll steps value. The resulting value is a value between 0 and 255 based on the current scroll state. Now, we'll create a new color using the fromNonPremultiplied method, using our color add variable for the red component. The other components stay 0, except for the alpha component. When we build and run this game now, we can see that everything is the same, but when we press the right mouse button, our red dot changes to black, meaning that our current scroll wheel value is 0. Scrolling the mouse changes the color from black to red over an interval of 12 scrolls. In the next video, we will use the keyboard to manipulate the white dot. In this video, we will use the keyboard input to manipulate the white dot. We start this demo with code from our empty input scene that we made in the previous video. XNA provides a static class called keyboard. This class contains a method called getState. When we call this method, we retrieve an object of type keyboardState. This object contains several methods to check the state of a key. SKeyDown and SKeyUp, both taking one argument of type keys, an enumeration of all the possible keyboard keys, will return true or false if the key is currently up or down. There is also a method called getPressedKeys that returns an array of keys that are currently pressed. We can also use the index operator using a keys object as index, and this returns the key state of that key. Key state is an enumeration containing two values, up or down. We will use the SKeyDown method to check if the spacebar is currently pressed. If that's the case, we change the dot color to red. And again, we need to reset the dot color each frame. If we don't do that, the color of the dot stays red after pressing the spacebar once. When we build and run this game, we can see that the color of the dot changes to red when we press the spacebar. Now we will move the dot 20 pixels to the right when the Enter key is released. If a key is not pressed, its state is always up. So we need a way to check if the key was pressed the frame before. We do this by creating an extra field of type keyboardState. Call it previous keyboardState. At the end of each update, we will set this value to the current keyboard state. This way, we have access to the previous keyboard state in the next frame. And now we can check if the Enter key is released in the current frame. So, if the Enter key was pressed in the previous frame and it's not pressed in the current frame, we add 20 pixels to the X component of the dot position. When we build and run this game, nothing happens when we press the Enter key, but only when we release the key. We can also use the getPressedKeys method to retrieve an array of currently pressed keys. This way, we can iterate that array and use a switch statement to check several keys. In this example, we check if one of the arrow keys is pressed and move the dot position 5 pixels to the corresponding direction. When we build and run this game and press one of the arrow keys, the dot will follow that direction as long as we press the key. In the next video, we will use gamepad input to manipulate the white dot. In this video, we will use the gamepad input to manipulate the white dot. We start this demo with code from our empty input scene that we made in a previous video. XNA provides a static class called gamepad. This class contains a method called getState. And this method takes two arguments, a player index and a gamepad dead zone. For now, we will use playerIndex.1, but you can use up to 4 different gamepads. Gamepad dead zone is an enumeration containing 3 values, circular, independent, and none. The dead zone is the zone when the thumbstick are supposed to be at their 0 position. Using GamepadDeadZone.none gives us the raw values without processing. These values can be a bit noisy around the dead zone. GamepadDeadZone.circular processes the values taking both axes into account. This is important when using the thumbstick for aiming, for example. GamepadDeadZone.independent processes the values independent from each thumbstick axis. This type is mostly used for moving a character or object. For now, we will use GamepadDeadZone.circular, and this method returns an object of type GamepadState. This object contains several properties representing all the buttons, thumbsticks, and triggers on the gamepad. Also 2 methods, sButtonDown and sButtonUp, to check if a button is down or up. These methods work the same way as the sKeyDown and sKeyUp methods of the keyboard state. Thumbsticks property contains both thumbsticks, the left one and the right one, and each thumbstick has an X and Y property, representing the thumbstick's position on each axis. These values range from -1 to 1. The triggers property contains also both triggers, the left one and the right one. Each trigger returns a float value. Because the triggers are pressure sensitive, this value ranges from 0 being not pressed to 1 being fully pressed. Sometimes it's possible that the gamepad is suddenly disconnected for some reason. So before we use the input, we check if the gamepad is connected. Only then we can use its input. Now we will move the dot based on the position of the left thumbstick. We start by positioning the dot at the center of the screen. Multiplying the X component of the trigger with the half of the width of the screen, the same as windowCenter.x, gives us the offset on the X-axis. We do the same for the Y-axis, but now we use the negative Y component multiplied with windowCenter.y. A bit more information about this calculation. We want to transform the thumbstick coordinate system to our screen coordinate system. When our thumbstick is at the center, the coordinates are 0, 0, resulting in a screen coordinate of 640 by 360. Then, if our thumbstick is up, the thumbstick coordinates are 0, 1, resulting in a screen coordinate of 640, 0. If our thumbstick is down, the thumbstick coordinates are 0, -1, resulting in a screen coordinate of 640, 720. Now, for the x-axis, if the thumbstick is left, the thumbstick coordinates are -1, 0, resulting in a screen coordinate of 0, 360. And finally, if the thumbstick is to the right, the thumbstick coordinates are 1, 0, resulting in a screen coordinate of 1280, 360. When we build and run this game, the dot follows the position of the left thumbstick. Now we will use the right trigger to change the color from black to red based on the trigger pressure. We can create a new color using the fromNonPreMultiplied method of the color class. There are 4 arguments: the red, green, blue, and alpha component. Each component has a maximum value of 255. Multiplying this value with the right trigger pressure for the red component gives us a color between black and red based on the trigger pressure. The green and blue components are 0, except for the alpha component that needs to be 255. When we build and run this game, the dot's color changes from black to red when we press the right trigger. And finally, we'll change the color when the gamepad is disconnected. So, we've already have if statement that checks if the gamepad is connected. And when we add an else to that statement, we can write code that triggers when our gamepad is disconnected. So inside the else statement, we'll set our dot color to green. Now, when we build and run this game, our dot is black, meaning that the gamepad is connected. From the moment we disconnect our gamepad, the dot turns green, because our gamepad is now disconnected. After we reconnect the gamepad, the color of our dot turns back to black. In the next video, we will have a look at the logic behind an input manager, a system that makes input handling a lot easier and maintainable. In this video, we have a look at the logic behind an input manager and use it to manipulate the byte dot. It's always a good idea to give the user multiple ways of controlling the game. Some users prefer playing with the gamepad, while other users prefer mouse and keyboard. Adding all these preferences to the game makes the code look like a mess. That's why we will add a system that manages our input, keeping the code simple to use and, more important, maintainable. Let's have a look at the code of the input manager. We start by defining 2 enumerations, one representing all the mouse buttons, because we've already have an enumeration for the keys and gamepad buttons, and to keep things consistent, we create this one for the mouse buttons. The second one is a trigger state enumeration, containing the possible states of a button. Pressed is being up in the previous frame and down in the current frame. Released is being down the previous frame and up in the current frame. Down is just being down in the current frame, and up is being up in the current frame. Next, we have a static class mouseStateExtended that contains several mouseState method extensions. To keep things consistent with the keyboard state and gamepad state, we've added an isButtonDown and isButtonUp method to the mouse state. The second class is inputAction. Each time we want to bind a key to some action, we need to create an input action. This input action has an ID, optional button properties for each input device, the state when this action needs to be triggered, and a value that indicates if the action is triggered in a current frame. So input actions can be triggered by a button from multiple input devices. The input manager class does all the hard work for us. It contains a dictionary of actions, and for each input device the current and old state. The first method, mapAction, will add an input action to the dictionary. If the ID already exists, the corresponding input action is overridden. getAction returns the corresponding input action if it exists, based on the ID that we need to pass as an argument. isActionTriggered returns true or false if the corresponding action is triggered, false if it doesn't exist. And finally, the update method, the heart of the input manager. We start with filling up the old states with the current states. And after that, we fill up the current states with the new states of each input device. Then, we iterate the input action dictionary and set each its triggered property to false. We check the action based on the action's trigger button state. If its trigger state down, we check if the corresponding button is down in the current frame. If its trigger state pressed, we check if the corresponding button is down in the current frame and was up the frame before. If its trigger state dot released, we check if the corresponding button is up in the current frame and was down in the frame before. Else its trigger state dot up. And then we check if the corresponding button is up in the current frame. Running this update each frame will give us the correct input state for each action. Let's implement this input manager in the game class. We add an extra field of type input manager and call it input manager. We also initialize it immediately. To keep things readable, we have to create an enumeration of action. This will be used as ID for the input actions. We need two actions, go red and move. In the initialize method, we create two input actions. A new input action for the go red action that triggers when the corresponding buttons are down. In the object's initializer, we assign a button for each input device, the A button on a gamepad, the left button on a mouse, and the spacebar on a keyboard. The last thing we need to do is add this input action to the input manager using the map action method. We do the same for the move action, but here we use action.move as ID and set the trigger state to released. We use the left thumbstick right on the gamepad, the right button on the mouse, and the right arrow key on the keyboard, and add it to the input manager. The input code is very simple now. We need to update the input manager each frame by calling the update method. And we also have to reset the dot color each frame back to white. To test if an action is triggered, we use the isActionTriggered method of the input manager. If our go red action is triggered, we change the dot color to red. If our move action is triggered, we add 10 pixels to the X component of the dot position. This code is a lot simpler and more readable than it would be without the input manager. When we build and run this game, we see that the color is changing when we hold the A button, the left mouse button, or the spacebar down. And the dot is moving when we press and release the right mouse button or the right arrow key, or when we move the left thumbstick to the right. So let's have a quick overview of the input manager that we've just implemented. Our input manager manages several types of input: the mouse, keyboard, and gamepad. It will determine the state of a certain button of one of these devices based on the current and previous state of the device. If you want to check if a certain button is triggered, we need to add an input action. We can also add several input actions to the input manager. Each input action has its own set of buttons to check. So checking for input becomes pretty straightforward and always the same. First, we create an input action and give it an ID and a button trigger state that tells the input manager when this action has to trigger. Then, we need to define the buttons we want to use for this action. And the last step is adding it to the input manager, using the map action method of the input manager. This way, our input manager knows about the input action. Then, we use the input manager.isActionTriggered method with the ID of the input action you want to check to retrieve a boolean. And this boolean indicates if our input action is currently triggered. A simple and straightforward system. In the next video, we go over various ways of playing sounds for your game.
In the previous section, we've covered input. In this section, we'll play audio, because this will help set the mood for our game. In this video, we'll start by playing regular audio. In the content project, you can see we added a wave file called jump.wave. We can see it uses the wave audio file importer and uses the sound effect processor. By default, we can load MP3 files, WAV files, and WMA files. Now we will play our jump.wave. So let's write some code. We need to add two fields, one of type sound effect, this will be our jump sound, and one of type integer. This will be a counter. We will play the jump sound each 100 frames. In the load content, we can then load the sound. We can do this by using the content manager. As type, we specify sound effect. The path to the file is jump. We can then go to the update method where we will play the sound each 100 frames. The first thing we'll do is increment our counter. Then we will check if our counter reached 100. If it did, we will set our counter to 0 and play the sound. We can play a sound by calling play on the sound effect. If we then run the project, we should hear the sound every 100 frames. The play method of the sound effect class has another overload where we can specify the volume, pitch, and pan. The volume is a float value that ranges from 0 to 1. Complete silence is 0 and full volume is 1. The pitch, or the frequency of a sound, is a value ranging from -1 to 1. The normal pitch is 0. -1 is an octave down and 1 is an octave up. The pan is a value ranging from -1 to 1. Again, 0 is the normal situation, being centered. -1 plays fully through the left speaker, and 1 plays fully through the right speaker. We will now play our jump sound, half the volume, 1 octave higher and fully through the left speaker. The problem is that a sound effect is kind of a one-shot deal. You play the sound and forget about it. You can't modify it afterwards. There's another class called sound effect instance that will offer us more control and also allow us to loop the sound. So let's delete the code we've just written and use a sound effect instance. We'll need to add another field. We can delete the counter and create another field of type sound effect instance. We can call it jump instance. In the load content, we can then create our jump instance using the jump sound. A sound effect has a method called create instance. We can use that method to create an instance of the sound effect. You can create multiple instances of one sound effect. A sound effect instance also has properties for setting the volume, pitch, pan, and looping the sound. Again, we will set the volume to half the volume, the pitch 1 octave up, and play fully through the left speaker. We will also loop the sound. Finally, we can call play on our jump instance. You can even do this in the load content. If we then run the project, we should hear the sound looping. Using this method, we can also change the volume, pitch, and pan while the sound is playing. So it offers us more flexibility. That's it for this video. In the next video, we'll play 3D sounds. In the previous video, we've played sound. In this video, we're going to play 3D sound. That way, it will appear as if the sound comes from a specific location. We've added an extra sound to the content project of this demo project. You can see it here. It's called Explosion. The implementation of a 3D sound is very similar to using a sound effect instance. Because of that, we've already implemented the sound effect instance in this code. Beside that, we need to add two extra fields, an audio emitter and an audio listener. The emitter represents the objects that will cause the sound. For instance, in case of an explosion, that will be the bomb. The listener is the object that hears the sound. For instance, that can be the player's position. We can then go to the load content. There we will create a new emitter and a new listener. We can do this by using their default constructors without arguments. Then, we can apply the emitter and the listener to an instance of a sound. We can do this by calling apply3D on our explosion instance. The method has two arguments, being the listener and the emitter. Note that we do this before we call play on our explosion instance. Okay, if we were to run our project now, our sound would be playing, but it wouldn't appear as if it was 3D sound. That's because the position of our emitter and our listener is the default position, so we didn't change it. Let's go to the update and change the position of the emitter each frame. We will use a sine function along with the game time to move the emitter. After we change the position of the emitter, we need to apply the 3D effects to our instance again. We do this with the apply3D method. If we run our project now, we will hear the sound of our explosion and it will be moving around in 3D space. In the next video, we'll play songs using the media player. So in the previous videos, we've played sounds. There's also a possibility to play songs from the user's media library. We'll do that in this video. Let's go to the code. We need to add a field. The field will be of type media library. We will use this field to access the user's media library and play his songs. We can then go to the initialize. There, we will first check if our game has control over the media player. So, if we can play songs using the user's media player. We will also check if the current library contains songs. If so, we will play the first song from the user's library. If you press F5, you should hear the first song from your library. On Windows, the media library can only find songs if Windows Media Player previously found songs on the system. For more information about Windows Media Player, take a look at the references. The static media player class exposes more functionality. It allows us to play songs, pause songs, resume songs, play the next song, play the previous song, and so on. It also has several events, for instance, if the active song changed or if the media state changed. Our library also has specific functionalities. For instance, now we play the song, but we can also access albums, artists, and playlists. In short, we have full control over our media library. There's one more thing we need to do. When the game is closing, we need to stop the media player to prevent music from playing after the game has finished. We can do this by calling stop on the media player class. That's it for this section. In the next section, we'll continue building our framework. We will then use that framework to build our game.
In the previous section, we've covered sounds. Our framework is almost ready. But there are still some things that we need to add. A game scene object is one of them. In this video, we will have a look at the advantage of a game scene. At the moment, we always managed our game objects in the main class. This way of working is a lot of work. First of all, we need to initialize the objects, load their content, update them, and draw them. If we had a project with a lot of different objects, this would be a lot of work. Second, keeping different screens, like the menu or the game itself, separately, without ending up with a jumble of code, is hard to achieve with the current system. That's why we'll add a new object, called a game scene. A game scene is a collection of game objects. The game scene contains several methods to manage those game objects. This way, we just need to manage this game scene in the main class, which, in turn, will manage the collection of game objects. For every screen, we can create a separate game scene. A menu will have its own scene, containing only the objects that are needed for the menu, like buttons and a background, while the game itself also has its own game screen. This way, our code stays clean, readable, and more important, maintainable. Let's have a look at the implementation of game scene in the current framework. This project is built upon the 3D graphics project we've made in a previous section. So the only class that's been added is the game scene class. There are also some modifications in the GameObject2D and GameObject3D classes. GameObject2D and GameObject3D now contain a property of type GameScene, called Scene. This way, you can access the game scene through the object itself. GameObject2D also gets an extra property, Draw in front of 3D, a boolean that indicates if this 2D objects need to be drawn in front or behind the 3D content. That's all. Now we can have a look at the game scene class. Every scene has a name and two lists. A list of GameObject2D objects and also a list of GameObject3D objects. In the constructor, we set the name property. This name is required. It will be used for identification later on. And we initialize both lists. We have overridden the equals method. This gives us the possibility of comparing two game scene objects. And because of this override, we also had to override the hashcode method. Of course, we can add and remove GameObject2D objects to the scene using the addScene object or removeScene object methods. AddScene object will add the object to the scene and fill up the scene property of the object. And removeScene removes the object from the scene and resets the scene property of the object. There are also overloads of these methods for GameObject3D objects. The other methods are all virtual. Activated is called when the scene is set as the active scene, but we need a scene manager for that. And deactivated is called when the scene isn't the active scene anymore. Then we have the managing methods. Initialize calls the initialize method of all the added objects. Load content calls the load content method of all the added game objects. Update calls the update method of all the added game objects. Draw2D is the draw call for GameObject2D objects. Based on the draw in front of argument, the corresponding GameObject2D is drawn. And finally, Draw3D. That's the draw call for GameObject3D objects. That's all for the game scene class. Let's have a look at an implementation of this class. We've created a new class called TestScene that inherits from GameScene. It has two objects, a background and a model. First of all, we pass the name of the scene to the base class. Then, inside the overridden initialize method, we initialize the background and the hero, and add them both to the scene. Note that we set the draw in front of 3D property of our background to false. This way, the background is drawn behind our 3D content. That's all. Our TestScene class is ready to be implemented in the main game class. In the main game class, we need our render context and also a TestScene object. Like before, we set the width and height to 1280 by 720. We initialize the render context and set the camera property. And we also initialize the TestScene class and call the initialize method. In the load content method, we set render context.spriteBatch and graphics device. We also need to call the load content method of the test scene. In the update method, we set render context.gameTime, update the camera, and call the update method of the test scene. The draw method is divided in three parts. First, we draw all the 2D that needs to be drawn behind the 3D content. We do this by calling the draw2D method and set the draw in front of 3D argument to false. We do that between the begin and end method of spriteBatch. And we also need to reset some render states afterwards. The second step is drawing the 3D content by calling draw3D of the test scene. And finally, the last step is drawing all the 2D in front of the 3D content by setting the draw in front of 3D argument to true. And again, we do that between the begin and end method of the sprite batch. So now we have our main game that contains a game scene called test scene. This scene contains two objects, a background and a model. When we build and run, we can see our background and the model. In the next video, we'll have a look at hit detection. In this video, we'll add another game object to the framework, Game Hit Region 2D. This object helps us with hit detection. When we are building the game, we'll also use this object to do the collision detection, but that's for another video. Let's have a look at that class. The GameHitRegionToD class inherits from GameObject2D. It contains a property of type color. When we want to see the actual hit region, this will be its draw color. It also contains a field of type rectangle, the actual hit region. The constructor contains two optional arguments, a width and a height. Both are optional and default 0 when they aren't set. So it's not required to give the hit region a dimension on initialization. But if one of the arguments is 0, we set hitRect to rectangle.empty. Else, we use the given width and height. And next, we set the draw color to red and canDraw to false. If canDraw is true, we will see a border around the hit region in the predefined color. The setDimensions method changes the dimension of the hit region. Then, there are several hit test methods. We can do hit test based on an X and Y coordinate, or we can also do a hit test using other GameHitRegionToD objects. The intersection method checks if the region of two GameHitRegionToD objects intersect and returns the intersecting area. The update method will set the hit region's location based on the world position. And if canDraw is true, we will use the debug2D class to draw a rectangle that represents this hit region, using the hit region's rectangle and draw color as arguments. The static debug2D class is a simple helper class that makes it easy to draw lines and rectangles. This way, we can actually see our hit regions. This makes debugging a bit more easy. And that's why it's called debug2D. Let's have a look at it. Debug2D uses a texture that's just one white pixel. And each time we want to draw a line, we store this line as a debug line object. This object contains the start and end points and the color. In the draw method, we draw all the lines at once by calculating the length and rotation of the line. We can use the sprite batch to draw this line. And that's all for the debug2D and GameHitRegionToD classes. Let's create a hit region in the test scene. We will update the test scene and add a GameHitRegionToD object. When the mouse is inside this hit region, we draw the background. Otherwise, we don't draw the background. Create a new field of type GameHitRegionToD. Call it hitRegionn. Then, initialize this hit region with a width and height of 150. After that, we translate the hit region to a position of 565 on the x-axis and 285 on the y-axis. This way, the region is centered at the middle of the screen. Set the canDraw property to true. This way, we'll see our hit region. And the last thing we do is adding the hit region to the scene. In the update method, we need the current mouse state, using the getState method of the static mouse class. The canDraw property of the background is equal to the result of the hitTest method of our hit region using the current mouse state X and current mouse state Y as coordinates. Before this will work, we need to do some extra things in the main game class. First of all, we set our mouse visible by setting the isMouseVisible property of the game to true. We do that in the constructor. Second, we need to call loadContent of the debug2d class. This way, our white pixel texture is loaded. And finally, we need to call the draw method of the debug2d class. We do that at the end of the entire draw cycle, but still between the begin and end method of the sprite batch. This way, the hit region borders are always in front of everything else. When we build and run this game, we can see that the background is drawn when the mouse is inside the hit region. In the next video, we'll have a look at a simple menu scene. In this video, we'll implement another scene, the menu scene. But before we can create this menu, we need some buttons. Let's have a look at the GameButton class. The GameButton class inherits from GameSprite, because a button is also a sprite, with the only difference that we can click on it. This class has 3 events: onClick, onEnter, and onLeave. Also 2 Boolean fields. A spritesheet indicates if we use a spritesheet for the button. This way, the button's appearance changes based on its state. The spritesheet contains 3 images for the button: a normal state, a hover state, and also a click state. The second Boolean, is hovered, indicates if the mouse is currently inside the button's hit region. Then, there are several nullable rectangle objects. Rectangle defines a region of the spritesheet, a region for the normal, hover, and pressed state. And the last field is of type GameHitRegion2D, the button's hit region. The constructor has 2 arguments, the path of the asset and a boolean that indicates if that asset can be used as a spritesheet. Because this class inherits from GameSprite, we need to pass the path of the asset to the base class. Inside the constructor, we set the isSpritesheet property, initialize our hit region, and add it to the object. Inside the loadContent, we check if this button uses a spritesheet. If it does, we set the correct dimensions of the hit region and initialize the rectangles. Dividing the height by 3 gives us the correct height. If it doesn't use a spritesheet, we just set the hit region's dimensions to the total width and height of the sprite. Inside the update method, we will check the state of the button based on a current mouse state. We retrieve the current mouse state from the input property of the render context. This input property is our input manager that we've covered in a previous video. Adding it to the render context makes sure that every object has access to it. If the button is currently not hovered, we do a hit test using the current mouse position. If the mouse is inside the hit region, we set the isHovered boolean to true and invoke the onEnter event. We also set the current drawRect to the hoverRect. When the button was already hovered, we retrieve the current and previous button state of the left mouse button. Then, we do a hit test to check if the mouse is still inside the button's hit region. If it isn't, we set isHover to false and invoke the onLeave event. We also need to set the drawRect back to the normal draw region. But if the mouse is still inside the button's hit region, we check if the left mouse button is pressed in the current frame. If it is, we set the drawRect to the pressed draw region. Else, if the left mouse button is released in the current frame but was pressed in the previous frame, we know that the button is clicked. So, we invoke the onClick event and set the drawRect back to the normal draw region. That's all we need to do for the GameButton class. Let's have a look at the MenuScene class. MenuScene inherits from a GameScene and contains a background, a start and exit button, and also a sprite that represents the cursor. We pass the name to the base class in the constructor, and also initialize every object in the initialize method. The sprites of the buttons can be used as a sprite sheet, so we set the isSpritesheet argument to true. Inside the update, we use the mouse position as position for the cursor sprite. This way, our sprite acts like a cursor. Now, it's time to implement this menu scene in our game scene. The implementation is very similar to the test scene class we've seen in the previous video. We create a field for it, initialize it in the initialize method, and call its own initialize method. We call its loadContent method in the loadContent method, and in the update method we call the update method of our input manager and also the update of the menu scene. And we end by drawing the scene in the draw method. That's all. When we build and run this game, we see a background, a cursor, and two buttons. The button's appearance changes when we hover or press one of the buttons. In the next video, we'll have a look at a system to manage all our different scenes, the Scene Manager. In this video, we'll have a look at the Scene Manager. This is a static class that manages all our scenes. Every scene needs to be added to the Scene Manager. The Scene Manager takes care of initializing, loading content, activating, deactivating, updating, and drawing all the scenes. But only one scene can be the active scene, and it's only this scene that is updated or drawn. Let's have a look at the code of the Scene Manager. The Scene Manager is a static class. This way it can be accessed from every class. There are several properties. Main game is of type game and contains our main game object. This way we can access the properties of our game from everywhere. Then we have a list of game scenes and also the active scene, of course of type game scene. Our render context that needs to be passed as an argument in several methods, and a property of type input manager called input. This is just a link to renderContext.input. This keeps the code a bit shorter and cleaner when we want to add input actions. Inside the constructor, we initialize the game scene list and the render context. We also initialize the renderContext.camera and renderContext.input properties. The addGameScene method adds the given scene to the game scenes list, if it doesn't contain it already. And the removeGameScene method will remove the given scene from the game scenes list. If the given scene was our active scene, we reset active scene to null. The setActiveScene method will retrieve a scene based on the scene name we pass as an argument. If the scene exists, we check if there is currently an active scene and call the deactivate method. Then we set the active scene property to the chosen scene and call the activate method. At the end, we return true if the chosen scene exists, otherwise we return false. The initialize method will initialize all the added scenes. The load content method will call the load content method of all the added scenes, and also call the load content method of our debug2d helper class. In the update method, we check if there is an active scene. We update the game time property of our render context with the updated game time and call the update method of the input manager. And finally, we update the active scene. In the draw method, we draw the active scene if there is one. First, the 2D that needs to be drawn behind the 3D content. After that, the 3D content itself, and at the end, the 2D that needs to be drawn in front of the 3D content. And we also call the draw method of the debug2d helper class. Now, we need to implement this scene manager in our main game class. We can delete all references to the scenes we've made in the previous videos. First, in the constructor, we set the main game property. Then, inside the initialize, we add our two scenes to the scene manager, the test scene and the menu scene, and set our menu scene as active scene. At the end, we call the initialize method of the scene manager. In the load content method, we set renderContext.SpriteBatch and renderContext.GraphicsDevice and call the load content method of the scene manager. Inside the update, we just call the update method of the scene manager. And in the draw method of the scene manager. And that's all. But before we test this game, we need to tie up some loose ends in our menu scene and test scene. In the menu scene, we will set the test scene as active scene when we press the start button, and exit the game when we press the exit button by calling the exit method of the main game. In the test scene, we add an input action to the input manager that triggers when we release the escape key. Inside the update method, we set the menu scene as active scene when our input action is triggered. That's all. When we build and run this game, we see our menu scene. And when we press the start button, we go to the test scene. Pressing the escape button sets the menu scene active. And pressing the exit button exits the game. In the next section, we'll use our fully functional framework to build a game. In the previous videos, we've created our basic framework. In the following videos, we use our framework to create a simple 3D puzzle game. Let's start by taking a look at the game itself. We'll create a simple puzzle game, starring our little vampire friend. The first thing we see is the menu scene, with a start and exit button. This is the same menu we made in the previous video. When we press start, we go to the level scene and are ready to play the game. The goal is simple: lead the vampire to the exit by opening or closing several doors. The user can activate or deactivate a trigger by placing the hero in front of it and press the X key on the keyboard or the X button on the gamepad. And a trigger controls one or more doors. Changing the state of a trigger will open or close the door that is linked to the trigger. The hero himself can also perform some actions. We already know that the hero can change the state of a trigger when he's in front of one, but he can also walk and jump. Note that we also need to implement some basic physics, like collision detection and gravity. There is also a button to reset the entire level. When we press that button, every object is reset to its initial position and state. When the hero reaches the finish, we switch to another scene, the finish scene. This is a simple scene that shows a finish sprite. When we press the spacebar or the A button on a controller, we jump back to the menu scene and are able to restart the game again. The level consists of multiple elements: a background, the hero, the finish, and also some level building blocks. There are 4 categories of level building blocks. First of all, there are the blocks. These are the solid blocks that collide with the hero and also used to define the layout of our level. Note that there is also an invisible block. This way we can create some kind of invisible wall. Another category are the receivers. In this case we have 2 of them, a sliding door and a flip bridge. These will only collide with the hero based on their current state, being open or closed. Then we have the trigger category. We also have 2 of them, but their function is the same. They both have an on or off state. They are also linked to 1 or more receivers and will switch the receiver state when their own state is switched. The last category is the props category. This category contains several items, but their only function is to decorate the level. The level itself is generated using an XML file that contains all the different blocks and their properties. So when the game starts, we start by parsing the XML file and add all the blocks to the level. The XML file also contains a position for the hero and the finish. With this information, we can create a fully functional level. This XML file is created by a little level editor that's included with the demo code. We'll have a look at the editor in another video. So now that we know how the game will work, we can start by building it. But before we do that, we need to do some preparation work. We will organize our game classes by adding folders and using namespaces. We need a folder called Game, and inside this folder we have our scenes and objects. The objects folder is empty, but don't worry, we'll fill it up in the following videos. The scene folder contains 2 scenes already. The menu scene, this is the scene that we've created in a previous video, and also a new scene called level scene. This is a scene where we'll parse the XML, build, update and draw the level. At the moment there is only a background added, with its draw in front of 3D property set to false, because we wanted to draw behind the 3D content. Note that all the assets files are added also in the content project. In the content project we've added the assets, also using different folders to keep the overview clean and simple. We have the folder for models, and this folder contains folders for each block category, being blocks, props, receivers and triggers. When we add the assets to the project, we have to make sure that the properties are set. For example, we have our vampire model, which is a model with animation, and our finish model, just a static model without animations. So we have to make sure that our vampire model is set to use the skin model processor, otherwise we can't use the animation, and that our finish model is set to use the default model processor. Then we have a folder called Sounds, with 4 different sound effects. We also have to set the correct properties. We want to use the sounds as a sound effect, so we need to set the processor to sound effect. By default, they use the sound processor. The last folder is the sprites folder. This folder contains all the sprites we need for the game. And in the root, we have our XML file. This is just a file that we want to parse, so we need to make sure that XNA doesn't build it to its own intermediate format. And we can do that by setting the build action to none. This way, the file will only be copied with the other assets, but won't be built or processed. That's all we needed to do. When we build and run our game, we see our menu scene. Pressing start switches our scene from menu to level. But at the moment, there isn't anything added to the level scene, except our background. In the next section, we'll start creating the game by building the base class of our level blocks. In the previous video, we've had a look at the actual game and did some preparations to start building our game. In this video, we'll create a class called GridElement. We will use this class as base class for all the level blocks such as block, trigger, receiver, and prop. To make things easy, we'll use an imaginary grid to place our items. This way, adding an element to the level is fairly simple. Just pass the row and column, and our GridElement class will do the calculation part. We know that each grid element will have a dimension of 48 pixels, and we also know that the width of our screen is 1280 pixels and the height is 720 pixels. With these parameters, we can calculate the exact position of a grid element based on the row and column. We'll define our three constants in our vampire puzzle class. Making them public allows us to access them from other classes. A public const integer for our window width being 1280, window height being 720, and grid cell size being 48. We can also use the window width and window height fields as values for the preferred back buffer width and height in the constructor of Vampire Puzzle. This way, we reduce the amount of magic numbers in our code. When we want to change the resolution of the game for some reason, we just need to change those values we've just created. Next, we'll have a look at our GridElement class. This class inherits from GameObject3D because all the level elements are 3D. Inside this class, we defined 5 properties. Hit region of type GameHitRegion2D. Note that this is a GameObject2D object, so we can't add it to this GameObject3D. That's why we need to update this object manually. IsCollidable is of type Boolean and indicates if the hero has to collide with this grid element. 2 kinds of models, an animated game model and a game model. Some of the level elements are animated and some of them are just static models. When we create the level elements themselves, we just need to use one of these model types. The last property is grid cell of type point. This property contains the row and column of the grid element. The constructor has 2 arguments, a row and a column. With this information we can calculate the position of the element in 3D space and also the position of the hit region in 2D space. We start by calculating its 3D position. The center of our 3D axis is located at the center of the screen, but our imaginary grid starts from the left top of the screen. If our grid element is set to row 0 and column 0, we don't want it to be positioned in the center of the screen, but in the left top of the screen. That's why we need to calculate an offset by using the row, column, width, height, and cell size parameters. For the X component, we start by calculating the position of the element by multiplying the cell size with the column. If we want to position our element at column 0, the result of the previous operation is 0. Then we need to transform this coordinate to a grid coordinate. We do this by subtracting the half of the width of the screen, resulting in -640. Because the pivot point of our 3D content is located at the center of the object and not at the left top, we add the half of the width of a cell, resulting in -616 for the X component. When we do the same for the Y component, with the row and height as parameters, we obtain the correct position. Next, we store our row and column value in our grid cell property and translate the grid element using our previous calculated coordinates. Then, we need to translate our hit region to the correct position. Because our hit region is of type GameObject2D, so 2D object, this calculation is easy. It follows the same logic as our imaginary grid. The 2D axis also starts at the left top. So we only need to create a hit region with a dimension of grid cell size and translate it based on the column and row. That's all for the positioning logic. In the update method, we need to update our hit region manually. That's because our hit region isn't of type GameObject3D, so we can't add it as a child of this grid element. The last method is a virtual method called reset with an empty body. Some of the level elements need to be reset. When we press a certain button, this will be the method that handles the reset logic of each element that needs to be reset. That's all we need to do for our grid element base class. Visually, nothing has changed. When we build and run the game, it's still the same. But we did a lot of work behind the scenes. This way it will be easier to implement the other objects. In the next video, it's time to add our first level element, the block. In the previous video, we created a class called GridElement. This class will be used as base class for all the different level building blocks. In this video, we'll have a look at the block class. A block element is a solid type. The hero can't cross this element. It's also used to define the level layout. The block class is located in the game.objects.gridElements namespace. Note that this GridElements namespace is added to the game.objects namespace. The block class itself inherits from GridElement. The block constructor has 3 arguments: a string that contains the path of the asset, a column, and a row. This column and row value is passed to the base class to calculate the position of this element, as explained in the previous video. Inside the constructor, we check if the asset file variable contains something, because we can't pass an empty string as argument. If it is empty, we don't create and add a model. This way, we have an invisible block element but still collides with the hero. If it isn't empty, we create a static model based on the asset file and add it to the object itself. We also set the isCollidable property to true, because this element needs to collide with the hero. And for debugging purpose, we also set the canDraw of the hit region to true. This way the hit region will be visible. And that's all for the block class. But we also need a camera to ensure that the level is shown correctly. There are 2 types of cameras, the orthographic and the perspective camera. For now, the orthographic camera will do fine, and this way our hit regions will fit the models. Our 3D models will look like 2D because there is no perspective distortion. When the game is finished, we'll switch to a perspective camera to add more depth into the scene. Creating an orthographic camera is fairly simple. We've created a new class called Fixed Orthographic Camera and set the projection matrix to an orthographic projection matrix that we've created using the static createOrthographic method of the matrix class. With the width and height set to the width and height of the screen, a near clipping plane of 0.1 and the far clipping plane set to 300. With these parameters, our camera fits the screen perfectly. Go from -640 to 640 on the x-axis and -360 to 360 on the y-axis. We also need a clean and simple way to tag or identify the different grid elements. That's why we've created a class called enumeration that we will use to add several enumerations. The first one is a grid element type enumeration, containing every type of grid element, being block, trigger, receiver, or prop. In a later video, we'll also add our input action ID enumeration. It's time to add all these new objects to the level scene. First of all, we need to have some kind of collection of all the asset paths of each level element. We'll use a dictionary with a grid element type as key and a value of type string that contains the path of the asset. Every level block in the XML contains an asset ID that corresponds with the ID of this collection of a certain grid element type. So we can use this dictionary as a lookup table to receive the corresponding asset path. Second, we need to add a list of grid elements that contains all the blocks, receivers, triggers, and props of the level. Because every element inherits from grid element, we can create one list of grid elements. Next, we add the orthographic camera to the scene by creating a new fixed orthographic camera, translated a bit to the back of the screen to make sure that our objects are properly shown and not clipped because the camera is too close to the objects. we add it to the scene and set it as default camera in the render context of our static scene manager class. The level scene also contains three new methods: create asset list and build level. Both are called at the end of the initialization method, and also the create block method. In the create asset list, we will fill up our grid elements assets dictionary, and we've already done that for the block elements. There are 5 assets that need to be added to the grid element assets dictionary. Note that we use gridElementType.block as a key. The createBlock method is a simple helper method that allows us to create a new block by passing the asset ID, column, and row. Inside this method, we create a new block element. We look up the asset path based on the ID, and we know that we have to search it using the gridElementType.block key, and finally pass the column and row. After creating this block, we add it to the scene and also to the grid elements list. The last thing is returning the block element. This way, we have the possibility to modify some properties after creation. In build level method, we'll temporarily create 4 blocks, each with a different asset ID. We'll place them almost in the middle of the grid at columns 11 till 14, and all on the same row, being row 7. When we build and run this game, we see 4 blocks in the scene, each with a different texture. That's because we used a different asset ID for each block. We can also see the red border, defining the hit region. In the next video, we'll add another level building block, the receiver. In the previous video, we've created our first level building block, the block class. In this video, we'll add another one, the receiver class. The receiver is some kind of gate that prevents the hero from going through. A receiver is controlled by a trigger, and a trigger can open or close a receiver. For this demo, we have 2 kinds of receivers, a sliding port and a flip bridge. Let's have a look at the code. We've added a new class called receiver that inherits from grid element. It has several properties and fields. A property called isOpen of type boolean that indicates if the receiver is open or closed. 2 fields, the initial isOpen state. This is used when we need to reset the receiver, and also a field of type sound effect, the receiver sound. Note that this field has a static access modifier. This way, all the receiver objects use the same sound effect. There is no need to load the sound for each receiver. The constructor looks almost the same as the block object, except for the extra boolean at the end. Again, an asset file, a column, and a row, and the last argument is the initial isOpen state. Inside the constructor, we create a new animated model object. We know that every receiver is animated, in contrast to the block where we used a static model, and also add the model to the object. We also don't need to check if the asset file is empty, because we don't want to create an invisible receiver. If we would pass an empty string, the code will crash. We could also write code to handle this exception, but in this case it's our own responsibility to make sure that we don't pass an empty string as argument. Normally the hit region is created in the base class, but we want to modify it a bit. The default hit region is a bit too big. The hero would hit it before even reaching the port. So we need to make it a little bit smaller. We'll use the half of the width and the same height, and we also need to align it to the center of the grid cell. For debugging purpose, we can set canDraw of our hit region to true. After that, we call the setState method and pass the isOpen parameter as an argument. The setState method will set our isOpen property and also the isCollidable property based on the value of isOpen. If our receiver is open, we don't want it to collide with the hero, but if the receiver is closed, it needs to collide with the hero, so the hero can't pass through. The last thing we need to do is playing the corresponding animation based on the isOpen state. We also don't want to loop the animation and blend it with a possible previous animation with a blend time of 1/10 of a second. Back to the initialize. After setting the state, we set the initial isOpen field to the isOpen parameter we received as an argument. And that's all for the constructor. There are also some other methods. The load content is used to load our sound effect, if it isn't loaded already. The switch state method will switch the current isOpen state, and also play our sound effect. Switching the state is easy. We just need to call the setState method with the negated value of isOpen. We use the negation operator to do that. The last method is the reset method, an override of the base class reset method. Inside this method, we only need to set the state back to its initial value. And that's all for our receiver object. Let's add it to the level scene. Inside the level scene, we need to do two things. Add the assets to the grid elements assets dictionary and add a create receiver method. Adding the assets is simple. We create a new array of strings with a size of 2 because we only have 2 receiver assets. Fill it up with the asset paths and add it to the dictionary using grid element type.receiver as key. The receiver method has 4 arguments: an asset ID, column, row, and the initial isOpen state. Inside this method, we create a new receiver object using those parameters and add it to the scene and grid elements list. The last thing we do is returning our receiver object. To test our receivers, we'll temporarily create 4 receivers inside our build level method. We'll place them on the same positions we used for our blocks. 2 times 2 receivers with the same asset ID, but with a different isOpen state. When we build and run this game, we can see our 4 receivers. 2 times the same receiver, but one is open and the other one is closed. Note that our hit region is smaller than the default size. In the next video, we'll add the trigger object to our project and link it to a receiver. In the previous video, we've created our receiver level element. In this video, we add another one, the trigger. A trigger is also an animated model with 2 states, on or off. But we can also link a list of receivers to the trigger. And when we switch the state of the trigger, we also call the switch state method of all the receivers that are linked to that trigger. We can also set a timer on the trigger, so that it is activated for a certain time and then deactivates itself automatically. Let's have a look at the trigger class. Again, our trigger element inherits from grid element and contains several properties and fields. First of all, we have a property called isOn of type boolean. This property indicates if our trigger is on or off. Then a float called flipTime. When the trigger is activated, it will automatically deactivate if this time limit is reached. When we pass 0 as flipTime, we ignore this feature. Receivers is a list of receivers. Those are our linked receivers. Then we have some fields. Initial isOn is used to store the initial isOn value that we use when we need to reset this trigger. Total flipTime is used to accumulate the total time between each frame. This way we know when our flipTime is reached. And last, our trigger sound, a sound effect that is played when the trigger switches states. Again, this field has a static access modifier, so that every trigger uses the same sound effect. We can only switch one trigger at a time. The constructor needs 6 arguments: the asset file, column, row, isOn, our linked receivers, and an optional argument flipTime, with a default value of 0. So default it's disabled. We also need to pass the column and row to the base class. Inside the constructor, we create our animated model based on the asset file and add it to the object. Then we recreate the hit region. Again, the same as our receiver object, we want to use a smaller hit region. We'll use the half of the width and the height of the normal hit region and translate it to the center bottom. For debugging purpose, we can set canDraw of our hit region to true. Then we set our receivers list, our flip time value and set is collidable to false, because this object doesn't need to collide with the hero, and also set our initial is_on value. The last thing we need to do is calling the setState method. The setState method has two arguments, the state we want to switch to and also a boolean that indicates if we only want to change the state of the trigger or also the state of the linked receivers. Note that this boolean is an optional argument and is false by default. Inside the setState method we set our is_on property. And if is_on is true, we reset the total flip time field to 0. This way we can restart the counting. If trigger only is false, we call the switchState method of our linked receivers. And at the end, we play the correct animation based on the state of is_on. Inside the loadContent method, we load our sound effect, only if it isn't loaded already. The switchState method will play our trigger sound and set the trigger state to the negated is_on value. In the update method, we check if the trigger is on and our flip time value is bigger than 0. In that case, we add the past game time to the total flip time value. If our total flip time value is bigger or equal than our flip time property, we deactivate our trigger by calling setState false. The last method is the overridden reset method. Inside this method, we set the state of our trigger to the initial is_on state. Note that we only want to set the state of the trigger, because when we reset, we will reset each element independently. That's all for the trigger class. Let's add it to the level scene. Like before, we need to add our trigger assets to the grid_element assets dictionary using grid_element_type.trigger as key. Then we create a new method called createTrigger. This method has 6 arguments: the asset ID, column, row, initial is_on value, a list of linked receivers, and our optional flip time. Inside this method, we create our trigger with the given parameters. We scale the trigger because the models are a little bit too small by default, and add it to the scene and grid elements list. The last thing we need to do is returning the created trigger. To test our new trigger, we will create a receiver and add it as a linked receiver to our trigger. And we also need to define an input action. When we press the spacebar, we will switch the trigger state. So, we've created a test trigger field of type trigger. And in the build level method, we created a receiver and also a trigger. We linked that receiver to the trigger. After that, we added a temporary input action that triggers when we released our spacebar. The last thing is switching the trigger state when the input action is triggered. We do that in the update method. That's all. When we build and run this game, we see our trigger and our receiver. When we press and release the spacebar, the trigger switches from state. And because our receiver is linked to the trigger, it also switches from state. You can also hear the sound effect when the trigger or receiver switches from state. In the next video, we'll add our last level element, the prop. In the previous video, we've created our trigger level element. In this video, we'll add the last one, the prop. Our prop element is only to decorate our level. It has no further function. Let's have a look at our prop class. Again, this class inherits from grid_element. It's a simple object. It takes an asset file, column, and row as argument, and passes the column and row to the base class. Props are static models, so we just create a game model based on the asset file and add it to the object. It is not collidable, and for debugging purpose, we set the hit region's canDraw property to true. That's all we need to do for our prop object. Now it's time to add it to the level scene. First of all, we add all the prop assets to the grid_element assets using the grid_element_type.prop as key. Then we've added a createProp method, taking an asset ID, column, and row as argument. Inside that method, we create a prop object, add it to the scene, and also to the grid elements list. And finally, we return the created prop. Now we can test this prop by creating props in the build level method. We created a prop for every asset file, 6 in total, and again we positioned them in the center of the grid, from column 10 till 15 and all on row 7. Each prop gets a different asset ID, ranging from 0 till 5. When we build and run this game, we can see all our props in the scene. So now is everything ready and set to build our level. In the next video, we'll parse the level XML and use that data to build our level.